values, right? But if you are applying your KCL and KVL right, then you should not be having a problem. Let's see what I'm saying. So if you see in the loop 4, you are seeing that you can apply or you can name this nodes or the voltages differently. Like I took AC here, right? This AC I took, this is plus minus, but when my current is entering, it will be minus VAC. You can take it as CA, but if you take it as CA, your C would be at positive potential. So it's up to you what you are taking, but you should be very careful that, I'm echoing actually. So you should be very careful that what you are writing should be fine, okay? Just a minute, sorry. So what I'm trying to say, if you follow the rule, or if you follow the KCL and KVL right, your answers, all answers should be same, even if you are following a different direction, okay? So I solved this complicated problem just to know that there could be scenarios where you are thinking that you are heading in the wrong direction, but you should be confident that, let's say, if you have found a quantity that is not needed, you will eventually find a quantity that is needed. So first of all, you need to progress in that direction where you will find that quantity that is needed, okay? So because we don't want to waste our time on the quantities that are not needed. So that's about it for this one. Now we will move towards another scenario, that is Y delta transformation. So what is Y delta transformation? So there are scenarios when the resistors are hooked up like that, that we cannot solve them using this, using the methods we know. Okay, there could be many other methods to solve them, but for now, the methods we know, we cannot solve them. So for these type of scenarios, we have some, conversions or transformations that we can do to solve them. Let's say that this is the circuit we have. This is called Wheatstone bridge. I'm not sure you will learn it some point or not, because it's used for different voltage measuring devices. So in this scenario, let's say this is your R6. In this scenario, what do you think? Which resistors are parallel and which are in series? This is a little complicated scenario in which it's hard to find or hard to simplify the circuit. So for these type of scenarios, we use delta Y transformation, okay? So simplification can be done by transformation. So what is it that delta Y transformation says? That if you have this circuit you can transform into it this circuit. So this is the delta like shape and this is Y like shape. So these are both interchangeable. So let's say if this is R1, R2, R3, and this is your A, B, and C. Okay, so R1, R2, and R3, A, B, and C. So for the similar nodes, A, B, and C, I will have resistors RA, RB, and RC. RA, RB, and RC are not equal to R1, R2, and R3. There are the conversion formulas that you can do, but you can replace this as Y. How you replace this? You will think that you are picking these three nodes, take them out of the circuit, and put them, these ones, in the circuit if you have to replace them. Okay, so that's how we think about them. That's how we can pick it up and replace the other. We will see the scenario in the example as well. So that's how it helps us to solve the circuit. Okay. Let's say if I just replace it here, if you think, if I just replace it in this circuit, if I say, after transformation, delta Y transformation, what this should be. So let's say I am replacing this delta, right? So I will be writing it as right? And then I'm having R4. So if you see this, I'm just trying to do this so that you can see that I just replaced these three nodes with R1, R2, and R3 with RA, RB, and RC, right? Can you see how is it becoming easier to solve this one now?
You could see what's in series and what's in parallel.
Yes, so you can see that these two resistors, are in series now. And similarly, these two resistors too, right? This one was R5, R4, and this is R6, okay? So these are in series. Right? But these are series, RB and R5 are in series, right? RC and R4 are in series, but they are parallel to one another because they have this node, right? So I can write RB and R5 are in parallel to RC and R4, right? Then they are in series with RA. So now you can see that how you can solve this circuit. Am I clear about that?
Yeah.
Yeah.
So that's why delta Y transformation helps us to solve the circuit, okay? But we need to know what is the transformation. Transformation is not a difficult thing, but I will not go into tedious, what you should say, the proof of it. So I'll just write how we can do the transformation. So there are two cases, or I'm not saying it's a case. If your RB, RC, and RA are different, they are not equal. And similarly, your R1, R2, and R3 are not equal. We call this an unbalanced case. So what I'm saying is, so the case number one, or scenario number one is when you have unbalanced case where your resistors are not equal, right? Okay. So in unbalanced case, R1 is equal to RA, RB plus RB, RC plus RA, RC divided by RB. So these formulas are also given in your book. R2 is RA, RB plus RB, RC plus RA, RC divided by RC. So you can see that in the above, we have all possible combinations and their sum and divided by the resistor. Okay, and R3 is RA, RB plus RB, RC plus RA, RC divided by RA. Okay, now this is R1, R2, and R3, which are in the delta combination. Now, what are the formulas for Y resistors? Okay, so RA is actually equal to R1, R2 divided by R1 plus R2 plus R3. RB is R2, R3 divided by R1 plus R2 plus R3. And RC is R1, R3, R1 plus R2 plus R3. You can either call it as this thing as our del sum, right? And you can call this thing as RY sum, just to simplify the scenario. So this is your Y resistors. Now, if you can see them, if they are equal, let's say they are one value, let's say they are 1 kilo ohms or just 1 ohms. So how this will turn out? So this will become 1 by 3, right? So that is the balance, that is called the balance scenario, in which if they are equal, then you can just write them easily. So case number 2 says that is the balance scenario in which you say that these are the Y resistors, right? And you saw that the Y resistor is equal to 1 by 3 R del, right? And similarly, if you see del resistor, this is your del resistor, it will be equal to, if they are all equal to 1, so it will be 3 by 1. So that is your del resistor is equal to 3RY. So balanced case means what we have said, that R1 is equals to R2 is equals to R3, or RA is equals to RB is equals to RC. So this is the balance case. Okay, am I clear about that?
Yeah.
Okay, so I just want to, or maybe I do it later. Okay, so let me talk about one more thing and then I will do the example about this, okay? So we talked about dependent sources in network, but I think we did not write down the steps to solve them. So I will just do it to make it clear that how we will solve dependent sources. So there are some basic steps to solve them, and I will write it down. So one thing is, when you are writing KCL, KVL, or any other rule, you treat dependent source as a normal independent source. What it means, I will show you. The other thing is, once you write KCL or KVL, treating them as an independent source, then you will write separate equation to show the relationship, okay? To equate then in the circuit, you need to try to keep unknowns equal to try to keep number of unknowns equal to number of equations so that you can solve them. So what it means, let's see. So in this circuit, you need to find in the given circuit, find V naught. Okay. So just confirm that, yes.
Is she frozen again?
Yep.
So tic-tac-toe?
Guys, what's the word?
F in the chat. F in the chat. F.
What?
F in the
What's
chat.
the word?
See it. Love to see it.
Oh,
Oh, she's gone.
Yeah, that third bullet, Sabrina, I don't know what that says either.
I took a screenshot of it, but I still don't get it.
It says number of equations equal to number of unknowns.
Okay.
That word was number. What? Okay, thanks, Aiden.
Probably like NO. I don't remember.
Sorry, we don't have time. Okay. Sorry for that. Okay, so I'm not sure why it happens. What is this best internet connection in this area? Do you know that?
Where are you at the school?
No, no, I'm at home.
Oh, you're at home. Well,
Yeah.
if you know where your router is in the house, it's probably the closest to where the router is.
So then it will be fine. It will be stable if I am closest to my router. That's
Yeah.
what you're saying.
Likely.
But what do you think is which provider is the best? I mean, in terms of services or in terms of what do you Verizon? Okay. Okay. So this is the network. I'm not screen broadcasting. So this is the network we are having. And in this network, we need to find V naught, okay? So can you tell what should I do to find V naught? What rule I should apply to find V naught? And this is 10 milliamps. Can you listen to me? Yeah, okay.
Yeah.
I thought I am again disconnected.
I was thinking.
Okay, yes. What do you think?
Oh, I said KVL.
What is KVL? In which you try to find the voltages in the
V0.
loop?
Trying to find V0. Yeah.
Try to find?
Am I cutting out again?
Yes, sorry.
All right.
I
Not even worth it then.
try to find voltage or try to find current. That's what my question is.
Voltage. V0.
Okay. Okay, that's fine. But if you see, the catch is that we have many loops, right? So if we try to find loop equation, then we have to find many loop equations, right? And if we try to find currents, then we have only two nodes, right? So let's see. This is our node because there is no other element here. And this is our node. So it's okay. I mean, if you try to apply the loop equation, and if you are able to find V not using loop equation, it's fine, okay? But I'm following the easiest route in which you are applying a nodal equation or KCL, okay? So apply KCL. And if in KCL, I'm saying that this node is V, okay? So it will be, the equation will be, can you help writing me equation what it should be? So 10 milliamps is fine. Then remember there is a dependent source as well, which is 4I naught. So I will write it as minus 4I naught because it's coming towards, like one is leaving and one is entering. The other is what? What is the other equation? So the other equation is V over 3 kilo ohms, right? Because this is one node. And then the second equation will be V over 6 kilo ohms, right? If this is V, the whole node. So you can see that in this equation, if this is a KCL equation, we did not try to solve what dependent sources. We just write it for I naught, what is given in the circuit, okay? We will figure it out later what it is, okay? But we need to figure it out. So how can we figure it out? What do you think, what should we do to say what I naught is? What I naught is, what do you think? And if we try to find I naught, will it help in this equation?
I'm sorry, I just have a quick question.
Yeah.
What does that say at the beginning of the equation in green? The LOM word? I just can't read that.
Sorry. It's so funny. This is 10 milliamps. Okay.
Thank you.
Okay. Now, what is I naught? Can you see I naught in the circuit?
Yeah.
Just
Right?
a question is does the one part say 4I naught?
Yes.
Okay.
But what I'm saying, if I replace I naught with something that I know, can it help the equation? So, yes.
Yes, because then you would only be solving for the voltage.
Yes, that's the point. And the other point is you will be solving, you have known what is your dependent sources. So what I tried in the above thing is that first you write the simple equation, then you try to replace what is your dependent voltage or current sources, okay? So my I naught is V over 3 kilo ohms, right? And if I replace this in this equation, it will become 10 plus, if all the scenarios are in millis, I will just write it in 10. And then it will become minus 4 V over 3 kilo ohms plus V over 3 kilo ohms plus V over 6 kilo ohms, right? And then I will just find out what my V is. And this V is becoming 12 volts, and this V is actually the same as this Vs, right? So it will become is equals to Vs as 12 volts. So, but I need to find V naught, not Vs. So how can I find V naught? But I need to know V for finding V naught.
Yeah, now that we know V and I naught, can we use KVL?
Okay. Any other hint? Okay. So if we apply KVL, let's say, so you know I naught, right? So you think that this 10 milliamps is dividing here, here, and here. And you know only the resistance, the current of the one branch, that is this one. You don't know the current of this branch, right? But you know the voltages of all nodes, like this one, right? So V is same in this branch, V is same in this branch, V is same in this branch, and V is same in this branch. Got it? So it means that we can use V to solve our scenario. Do you think that if I know this V, will it help me to find V naught? So this is V, the total, in this total branch, the voltage is V. What do you think 2 and 4 kilo ohms are in series or parallel?
Series.
Series, right? So if I know the total voltage across the branch, I can find out any voltage across 2 kilo ohms or 4 kilo ohms by applying voltage divider rule, right? So I will just do and this will be, V naught will be 4 by 6 kilo ohms into V or Vs, okay? So it will be 8 volts. Got it? So that's how you can find out your voltage. The important thing is just you need to know, I actually told it before as well, that if you see that there is no element in the upper circuit, right? Like here. So there might be a catch that you can apply KCL. It's not that you should apply KCL, but applying KCL may help you because there are only 2 nodes here and here that you need to consider, right? So you will know voltages across each branch and you can apply that information to find out your values. Am I clear about that? Okay, so I am solving a problem 2.84. I think this is from your problems, like the book problems. And in this network, you need to solve, find I naught in the network in figure problem 2.84. And all resistors are 6 ohm. So this problem says that you have so all resistors are, what you should say, 6 ohms, okay? And the current is 6 amperes, I think. Yes. Okay. So what do you think? Can you see that what should we do here? Is it the similar scenario you see delta y scenario? So can I write this as so can you see this as this? Can you write this as this?
Yeah.
Yes, so you can combine these just to give this a picture of the delta, right? So let's say if you just give this a picture of delta, I will just pick these 3 nodes and put my y in it, okay, to simplify it. So if I'm picking these 3 nodes, I will simplify this as no, I think I'm wrong here. So let's try to replace it. So this is y. Right? Is it good?
Yeah, looks good.
So these three points I replaced, okay? Now you can see that 2 resistors are in series and they are in parallel to others. So all of the resistors are 6 ohms, right? But these are not 6 ohms. So if these are 6 ohm resistors, like the delta resistors were 6 ohm, the Y resistors were not 6 ohms, right? So we need to find out what our Y resistors will be. So let's see. So if you know the delta resistor, you can find the Y resistor by 1/3, okay? So we know that these resistors were 6 ohms, right? But we need to find what Y resistor will be, which will be 6/3 is equals to 2 ohms. So now these resistors are 2 ohms and the other are 6 ohms, right? So the new circuit will be so you need to find the current in this branch, okay? We need to find the current in this branch, okay? So we know total current, right? This is 6 amperes, but we don't have any other information. We don't have voltage, otherwise we can just apply KCL, because this is one node up to find the current, right? We can still apply it, but I think first we should simplify the circuit if we can. So let's try to simplify it. So how can we simplify it? We know that these two branches are in parallel, right? So they will give us four ohms, right? Yes. Okay, so this will be 4, and the resultant circuit will be 2, 4, 6, and 6. So now you can apply KCL in it, but I think you know from the current division that when, like in voltage division, you said that you will apply what you should say, the voltage across that resistor. So if I have to find the current in this branch, I will use the resistors of this branch. So this is, let's say, RL. So this could be R1 or R2. So this could be RL divided by R1, R2 multiplied by 6 amps will give me I1 if this is I2. You see what my point is? Because we learned in current division that it's opposite of voltage division. In voltage division, the resistors across which you apply the volt, you want to find the voltage, you will use exactly that resistor. But in current division, you will take the opposite resistors. So that's why you are taking this. And that's why you will say 6, R1, R2, and RL should be in the bottom. So it's 6 plus 6 into 6. So this will give you I1. Three amps, right? So now I have 3 amps. That's good. But I don't have I naught yet, right? So which means I have the total current, that is this one, that is 6 amps. But I don't have I naught yet. So what I should do to find I naught? Do you think I naught 6 amp is dividing? Can I write this as this? Hmm?
Yeah.
So 6 amp is dividing, this 6 amp is dividing in these two branches, right?
Mhm.
Right. So I will apply again current division and try to find I naught.
Since both the resistances are the same, could you just divide it by 2?
Yes, I can, but I'm just trying to explain it that if they are not equal, then how you should do it, right? So I naught is equal to, if you want to find 8, what you should say, the current across this branch, you will use this resistor. So it will be 8 by 8 plus 8 into I1. So it will be 8 by 16 into I1, which is 3 amps. So it was 3 by 2, which is 1.5 amps. I know. Am I clear about that? Hello, can you listen to me?
Yeah. Yes.
Yeah.
Why
Professor,
my screen stopped? I don't know. 1 minute. Yes, go ahead.
Professor, I have a question. Isn't there a simpler way to solve this problem without having to go through all these steps so that you just solve for the current divider once to get I naught?
Just a minute. Let me show my screen again. Okay. So what you are saying is, let me quickly keep that again. Driving me nuts. Okay. Just a minute. Sorry. Okay, let me share my screen. Yes. Now you can ask what you're saying. So you are saying that is there a way of solving this, right?
Yeah.
So let's see. If you go up here, so you have 6 ohm resistors, right?
Yes.
So the simpler way is that I think and you think is that let's apply KCL, right? Or what is the simpler way
Yeah.
in your opinion? Or maybe try to reduce the
Yeah,
resistance.
I did it so that yeah, so what I did was the middle resistor, like I put two nodes there like B, A and B. And because like the resistance for the whole like circuit is all like 6, like I assumed the middle one would, the potential between node A and B is the same. So I got rid of it in the circuit. And then like I did
Can you
then with
show? Oh, I'm not sure. Can you share your screen or?
I can't because I like wrote it on paper.
Oh, it's fine. So what you are saying is that, let me clear. So this 6 ohm resistor, right? You get rid of that?
Yeah, because the potential between the two nodes is the same.
No, but there is a drop across this 6 ohm, right?
I mean, like the way I did it, I still got the same answer as like what you did for I naught to be 1.5 amps. Like once I got rid of that, what I did was with the resistor at the far end of the circuit, I added that with the other two resistors on like the second side of the node and like I did like a parallel resistor equation thing and I got that to equal to 4 ohms, and then I added it to the other two. It sounds confusing. Maybe I can like send this through
No, no,
email
no,
or
it's
something.
fine. What I will ask you to do, let's see. I think because these all resistors have equal values, then it's easy to imagine that the current will be half and the voltages will be divided. Let's see if this is not equal, right? If this is 4 ohms, right? Or some other value, then you cannot half the currents. You understand what I'm saying?
Yeah, yeah.
In that case, how you can get rid of this resistor? That's what my question is. Because this scenario we took, because this is easy scenario and it's easy to understand. That's why I just took these resistors, 6 ohms. But if they are not equal, then we have to find the voltage drop across it, right? We have to find the loop equations, right?
Yeah.
But what I'm saying is there could be many ways of solving it. If you think that this way can give me right answer and easy way to solve it, it's okay. You don't have to solve a circuit using one method. The only way I am trying to explain is that we need to learn every method. So in your bank, you have all the tools to solve it. You see my point? So you can use KVL, KCL, nodal analysis, delta Y transformation, anything that helps you to solve it. Okay?
Okay.
So it's up to you. I will not stop or say you cannot solve it like that. You can. Until and unless in the question I mentioned that using this method you solve it. Until unless you can solve it using any method. My idea is to provide you the tools or the ways to solve the circuit. But if you think that it can be easily solved using other method, it's up, you can do it. Okay? I just wanted to show that how you can apply delta Y transformation.
Yeah, okay.
Okay, so that's about it today. I just thought that I should not take more time. So I actually posted homework number 2, but I think in this chapter, you need to do a little bit more practice. So the more practice you will do, you will be able to solve more circuits. Once you are done with this chapter, this will help you a lot in the coming chapter. So you should do more practices of the problems and stuff like that. I will add one more example to the homework. I'll post it as separate exercise, I think. But other than that, I think this chapter is most important, and you need to do a lot more practice of try to do the examples and the homeworks too. I posted the solution of homework number 1, and that you can look into it. Okay, any questions you have?
I think when you posted the solutions for, oh, never mind.
What happened?
I think you posted the solutions to number 1 and labeled it as homework number 2 solutions.
Oh yeah, and another thing I did, I think I will change it. And another thing I saw, I was saying ENG 214. It's not 214, it's 212. I will change it. Okay, anything else? Are we good?
Yeah, I think we're good.
Okay.
Yeah, I think we're good.
Okay, so they look easy, but there are small things that you need to take care. So I'll just try like emphasize on doing it like in the mathematics you do. The more problems you do, the more fluent we are. So try to do as many examples as you can. Thank you very much for today. I'll post the quiz. Thank you.
Thank you.
Bye.
Thank you.
Thank you.